Okay, 3, 2, 1. All right, here we go. Let's get measurable. All right, so let's start off by noting that continuous functions have a framework to them. All right, so we spent a lot of time studying continuous functions so far, and let's point out that there's kind of like three big things about continuous functions. So the first thing is that there are these sets, open sets, that work well with continuous functions, and note that they have a set theoretic setup to them. That the empty set, the whole set count as open, unions of any size are open, and finite intersections are open. All right. And continuous functions are precisely those whose inverse images of open sets behave nicely. Specifically, the inverse image of an open set is the domain intersected with some other open set. So another way of thinking of that is, well, the inverse image of open sets are, in fact, open within their domain. And the third thing is what we just recently demonstrated, which is that if you have a sequence of continuous functions and they converge uniformly, then the limit is continuous. And we noted that you need the uniform part there. Pointwise does not ensure continuity. So naturally now, with this laid out here, you can kind of guess what we're going to do. What we want to do is mimic everything we see here. I have sets that have set theoretic behavior. I have functions that treat inverse images in a certain way. And what I really want, and as we saw, what really fails with the Riemann integral is that, well, there are things we can make pointwise limits of, but the pointwise limit fails to be integrable. Right? And continuity, while are not the only things that are integrable, continuity is a good starting point for a lot of analysis. We see that here we need full-on uniform convergence to keep things working, so our goal is to set up sets and functions that behave nicely with a hopeful sticking point of pointwise convergence, so we can hopefully fix the Riemann integral. All right. So, naturally, as the title suggests, what we'll start with are what we'll call measurable sets. Now, it's worth noting that there are vast varieties of measurable sets of different styles and types, Lebesgue measurable being the most famous, but there are other ones. And they're all built off of the idea of a sigma algebra. So this is a collection of subsets that has that adhere to some set theoretic rules. Specifically, the whole set is in there. Complements are in there, and note this complement is relative to the subset. So I've got a subset of real numbers, and I'm talking about sigma algebras within that subset. And finally, countable unions. So here we see kind of like what's going on with open sets, but a couple of key differences. So we do have the whole space, we only have countable unions, and now we're also throwing in complements. Interesting. All right. Now, of course, at first glance, I can just tell you what a sigma algebra is. You might look at it and go like, okay, why do we care about this? And this is one of those definitions where, right, the reason you care about this is made apparent by the theorems you can prove from it. And, right, this is not how this was discovered. People figured out the theorems they wanted and then realized that the sets they were working with had these properties. Similar to kind of, we pointed out historically, how uniform continuity was really discovered and its connection to compactness. All right. Okay. And, any element of a measurable set of a sigma algebra, these are usually referred to as measurable sets, or measurable with respect to the sigma algebra. Like I said, there are multiple sigma algebras floating around out there, and thus there are multiple different styles of measurable sets. For right now, we're going to work very abstractly. We'll get maybe a little bit more concrete later on. But anyway, so that's what we mean by a measurable set. These are just elements of a sigma algebra, and a sigma algebra is a collection of subsets that has set theoretic properties. So mimicking what's going on with open sets, but note without actually like giving a solid definition for anything, just sort of mimicking the, well, open sets have set theoretic properties, so I want things that have set theoretic properties. All right, well, let's note that from these three set theoretic points, we can actually demonstrate a wide variety of facts regarding sigma algebras. So they are closed under countable unions. They are also closed under countable intersections. The whole set is in there. Well, so is the empty set. Countable intersections and countable unions work well, so do finite ones. All right, nice. Complementing within a sigma algebra, so given an A and a B that belong to the sigma algebra, the complement of the two, or the set difference of the two, is in there. And the final point Ignore that these randomly turned into B's. There's a reason for that. We'll find out in the next video. Those are supposed to be M's. And the final point, if a set intersected with the subset of interest lands in the sigma algebra M, whenever it feels like correcting itself. Oh, God. Oh, it's still going. Great. Oh, there we go. Right. Then the complement of E within the real numbers, the intersection also works. And if this is immediately going, hey, if I knew, like, E was open, well, that would be closed. And vice versa, if I knew this was closed, that would be open. Whoa, maybe. All right. So, how do the proof of these things go down? Well, they're pretty straightforward. The first thing to note is that, well, complementing any set in a sigma algebra keeps you in the sigma algebra, and the union of that lands in there, but we know what a union of complements is. It's the complement of the union, and complementing that would then get, it's the complement of the intersection, and complementing that will get us that the intersection lands in there. Right, so again, no, it's just simply from De Morgan's law. Showing the empty set is in there is easy as well, just complement yourself. Now, for finite intersections and finite unions, all right, well, define a sequence where the first n terms are the elements out of the finite list, and then from that point forward, throw in the empty sets. All right, well, empty set is measurable, and all of the E's are assumed measurable, so the whole collection counts as measurable. So the union lands in the sigma algebra. And note that after n, then we're unioning the empty set, so after n, nothing is being added, and so we just end up with the finite union. All right, now that we know finite unions work, you can basically follow the same argument from point 1, where, well, then complementing and then complementing again will get you the intersection. Pretty cool. Or you can mimic a similar style proof here. Instead of using the empty set, you would use the whole space itself. All right, a set difference is pretty easy to demonstrate because note that you can rewrite this as this. It's a fun little set theoretic exercise for you to do. I'll leave that to you to fill in. That'll get you that the set differences land in the sigma algebra. Now, for the final point, suppose that if I have x intersected with E lands in my sigma algebra. All right, well, the complement would land in the sigma algebra. And again, the B's are showing up. Sorry about that. I thought I fixed all of those. I was using B's originally, and I'm saving that for the next video. So, yeah. That's what I get for copy and pasting, right? Okay, I think I fixed all of them. All right. Anyway, okay. The B will make sense. Trust you will not be borelled about it. It's not going to be borelling. Anyway. Okay, so then when you complement this, then you just kind of follow your nose on the set theoretic part of it, and you'll end up with x set minus E. But note that that would just coincide with x intersected with the complement, kind of a similar argument from up here. And there you go. That's in the sigma algebra, so it is measurable. And then vice versa, you'd pull the same trick. If you're in the sigma algebra, your complement's in the sigma algebra, then you just complement across and follow your nose on all the set theoretic things, applying De Morgan's law and some natural, like, how set differences work. And you'll get it. Hooray! All right, cool. So there we go. We have established measurable sets now. They are just elements of a sigma algebra, and we've now played around a little bit with how sigma algebras work. So let's introduce the notion of a measurable function with respect to a sigma algebra. And again, we'll mimic what we saw. Continuous functions are those whose inverse image of open sets behave, so same deal. We'll call ourselves measurable if the inverse image of an open set is a measurable set. That's all it is. All right. And now note again here, measurable with respect to the sigma algebra, of which there are many in existence. We'll talk a little bit more about specific ones in the next video. Like I said, right now we're going to go a little abstract. Okay. So let's start off with the classic, the example of a measurable function. So given any subset of your subset x, define the indicator function, chi of E, to be the function that's 1 for elements that are in E and 0 elsewise. Hey, that looks a lot like, the Dirichlet function, which we know fails to be integrable, and was like the first function we talked about in the class. Hey, look at that. It'd be great if that was measurable, right? And those were the things we can integrate? Yeah, that'd be swell. All right, and indeed, these things are measurable when the set they're indicating on is a measurable set. And this proof is super straightforward because, take a open set. So it's an if and only if. So suppose you are measurable. Okay, we'll take an open set U. The inverse image, note, because this thing only ever spits out 1 or 0, the inverse image is going to do one of four things. The open set misses 1 and 0, which means the inverse image is empty. The open set has 1 but not 0, which means it spits out E. The open set has 0 but not 1, which means it will spit out the complement. Or the open set has both of them, which means it will just give you everything. And note, all four of these things are measurable, so the inverse image of any open set will in fact be a measurable set. And conversely, suppose that the actual function is measurable, well, then we can find an open set that only has 1 in it, specifically this one, because we know the set's closed here. Oh, incidentally, we then know that singleton sets, and thus finite sets, are closed. So that's a nice little thing to point out and remember. Alright, and now that's open, and its inverse image is E, as already pointed out, guaranteeing that E is a measurable set. Pretty cool. Alright, so like I said, this is the quintessential example of a measurable function, but there are several other measurable functions floating around out there, and we'll talk about how we can make measurable functions from other ones. And note, our big landing here, as we've kind of already foreshadowed, is going to be that pointwise limit of measurable things remains measurable. But right now that may seem like pretty strange that we could pull that off, because we are assuming inverse image of open sets behave, but we already know that you need uniform convergence to get that to work. And we'll see that the slight modification of open sets property of any union and finite intersections to complements and countable unions, that little tweak is incredibly powerful. Alright, so that being said, let's start setting the stage for getting another more powerful definition for a function to be measurable. So we've defined it to be that the inverse image of open sets is an element of your sigma algebra. It turns out we can define that purely in terms of open rays. So in particular, the following 4 statements are equivalent. The inverse image of the open ray, starting at alpha, is measurable for all alpha. Now note, if you're continuous, the inverse image of this is open for all of them. The complement of this set, oh hey, remember we're a sigma algebra of complements. Then the inverse image of that, which would be this set, note the set of elements in X, so f of X is less than or equal to alpha, that's measurable for all alpha. Which is equivalent to, well, get rid of the closed and make it open. And then the complement of that. Hey, so all 4 of these are equivalent. If this set is measurable for all alpha, then so is this one, and this one, and this one, and vice versa. So if any one of these is measurable for all alpha, then all of them are measurable for all alpha. Alright, I wonder if we're going to prove that being measurable is equivalent to the inverse image of these things behaving correctly. That'd be nice. Alright, so how do we prove this? Well, there are 4 things that we got to prove are mutually equivalent, which means we really have 5 steps to do, and by 5 I mean, 4, and by 4 I mean really 2, because once you see how 2 of them work, you got all of them. So for the first one, we'll show why 1 implies 2. Well, if this is measurable for all alpha, as we already noted, well, what's the complement of this? It's precisely this set. So, and again, I got the freaking B. Put a B in the chat, boys. I have fun. I had them all fixed. This is great. This is what you get when you don't have any sleep. Anyway. Alright, so yeah. So if these are all measurable, then obviously the complements of all of them are measurable, so we're happy about that. Now, the tricky one is going from 2 to 3. So suppose that we knew that all the closed ones worked. Why do the open one work? Well, they work because the open one is equal to a countable intersection of the closed ones. And here's why you need the for all alpha. Right, so, note in this proof here, if you had one alpha that worked, then that alpha would work for the complement. But here we see to get the open part from the closed, this is why you need the all alpha. And obviously now when you inverse image this, that'll work. And from here now, proving 3 implies 4 and 4 implies 1, 3 implies 4 is basically the same thing as 1 implies 2, just the thing you started with was the opposite set. And same thing for 4 implies 1, you just mimic how 2 implies 3. Great. Alright, so now that we know that the inverse image of open and closed rays will be measurable, precisely if any specific type is measurable, we'll now get the classic criterion for a function to be measurable, which is that the inverse image of any open ray is measurable. So now note here the key difference. Open continuous functions required every open set. Measurable requires a specific open set. It requires the open rays. And as we just noted, that's actually equivalent to all the closed rays and the open rays in the other direction. But generally speaking, you work with this one. That's sort of classically the one you start with. Historically, I guess. I don't know. This one tends to work. It tends to be easier to work with this one, I feel like. I don't know. Maybe you like a closed ray. Maybe you like the open ray in the other direction. Go nuts. But alright, so now we see Measurable's key distinction between it and continuous, and again, now we're really seeing the power of sigma algebras as opposed to the collection of open sets. Alright, so the first direction's super easy, because if you're measurable, then these are open, and the inverse image is measurable. That's by definition what measurable means. So the converse is the fun. So suppose that we know that the open rays extending off to positive infinity are measurable for all alpha. Okay, by the previous proposition, that means we know the open rays going in the opposite direction are measurable for all, that should be a beta, not an alpha. Again, doing great here. Okay, and what do we know about sigma algebras? Well, they're closed under intersections, and note that would mean that the inverse image of open intervals is also measurable, because it's the intersection of measurable sets, and, oh hey, open ray going to infinity, open ray going to infinity, open interval, as we pointed out, if you have an open set, it is a countable union of things that look like that. And what's closed under countable unions? Oh, why sigma algebras? Oh, there you go. So, the inverse image of any open set is indeed measurable, thus your function is measurable if you know that it treats the open rays with respect. Alright, sweet. Okay, so now we see that measurable has this leg up on continuous, where you don't need any open set, you just need the open rays to be behaving. No, continuous functions have that property, but there are functions that fail to be continuous that will respect the open rays. They'll disrespect other open sets, but the open rays they respect. That's precisely measurable sets. Cool. Alright, and like I said, this is sort of the classic quintessential characterization for measurable functions. And to, now that we're equipped with this, we can go ahead and prove a bunch of facts about measurable functions. About how to make some measurable functions, shall we? Alright, so we have our set in our sigma algebra. If you've got a measurable function, then scaling it remains measurable. Constant functions themselves are measurable, so alright, so now we're getting some actual concrete examples of measurable sets. If you have a measurable function, then translating it is measurable, so adding a constant function. If you have two measurable functions, then this particular set is measurable, so the set of points where f of x is strictly less than g of x. And then we'll prove that the sum of two measurable functions is measurable, so that's kind of where all this is building up to. If you take a measurable function and square it, it remains measurable, and then the product of two measurable functions remains measurable. Cool. Alright, so pretty beefy list here of constructing measurable functions from our basic algebraic maneuvers. Before we go on, I do want to point out this one right here is the bane of my existence. The product of two measurable functions is measurable. On my analysis qualifying exam, so, when you go for your PhD, they make you take really obnoxiously difficult exams. This was a problem on it, and I tried proving it directly from the definition, the one we just proved, that open rays are measurable when you take their inverse images, and I, couldn't for the life of me figure it out. And then the person who was giving the exam, I asked him, how do you actually prove this? And he's like, oh, did you prove squares are measurable? And then I immediately got so mad, but I was like, oh my god. So, so let's build up to my favorite fact here. All right. So for scaling a measurable function remaining measurable, a couple of things. So first of all, if the scalar is positive, well, if you're looking at this open array, just send the scalar over. It's positive, so we can do that without changing the inequality, and the f's measurable, so these sets are measurable, meaning these are measurable, and there you go. If the scalar is 0, then you have the function that's constantly equal to 0, which, note, is actually equal to the indicator function for the empty set. Nothing lives in the empty set, so this function always spits out 0, and the empty set is measurable. So there you go. Okay, if the scalar is negative, then you do similarly to this, only now when you scale by 1 over c, it's going to flip the inequality, and we don't care, because as we noted, with measurability, it doesn't matter if it's open array is going to infinity, open array is going to negative infinity. All right, so that takes care of scaling a function. So now to prove that any constant function is indeed measurable, well, we'll pull the little trick we pulled here. Note the constant function 1 is the indicator function for the whole set, which we know is measurable. So the constant function 1 is measurable, and thus by 1 any scaled function is measurable, so any constant function is in fact measurable. Okay, and adding a constant to our function by a similar argument to this one right here, right, you can just subtract the constant over, and we know these are measurable by hypothesis, then true these are measurable, and there you go. All right, now for the fun one. So I'm going to prove that these are measurable sets, and the trick is to sneak in rational numbers in between them. Because since f and g are both measurable, that means these sets are measurable for all rational numbers. And note for any x, so that f of x is strictly less than g of x, there is some rational in between them. So that guarantees that our set of interest is contained in this countable union. And note that it's actually pretty easy to see that equality has to hold, because if you're in this set, then you're clearly in this one. Because if you're in this one, you're in one of these, and if you're in one of these, then f of x is strictly less than g of x. And hey, there you go, you've got a countable union of measurable sets, you're measurable. All right, and that's the key to prove that adding works, because if you look at this set, we'll subtract g over, and hey, you've got a translated measurable function. By the previous couple of points, we know that this function is measurable, and the previous point proved that this set itself was measurable, guaranteeing this is measurable, so the sum of measurable functions remains measurable. Real slick little argument, right? Yeah. Now for squaring, I'm not going to steal victory from you. That's going to be your third homework problem. So enjoy that one. And then from there, you can prove that producting will be measurable, because products can be written as follows. And note, we pulled this exact same trick for Riemann integrable functions. All right, sweet. So now that we've got algebraic things preserve measurability, let's now get to the star of the show, which is pointwise limits, and the way we're going to get there is by first showing that soups, imps, lim soups, and lim imps are all measurable. And it's worth noting that this is precisely the fact where continuous functions are not going to have this property. All right, and the trick to this one is to prove that the inverse image of an open array for a soup is actually the countable union of the inverse images of all the previous functions. And similarly for infimums, but you don't do the open arrays going to infinity, you do the open arrays going to negative infinity. All right, and this is going to give you the result, because note this will prove that soups and imps are measurable. And as we already noted, lim soups and lim imps are themselves soups and imps in disguise, so you'd automatically get it. All right, so we need to establish these facts here, and I'll prove the first one, and note that the second one is proven very similarly. All right, so if you're in the inverse image of the soup, that means the soup lands in this set. Okay, and remember, the soup of a function is the soup of the outputs of the sequence of the function at that given point. All right, and if the soup is in alpha, well, alpha is strictly less than the soup, so that means there has to be something from the list hanging out in between alpha and the soup, otherwise it wouldn't be the soup. All right, and hey, note that would mean that x is in the inverse image of that specific function. Hey, cool, there you go. All right, and for the converse, if you're in the union of all of these, all right, well, then you're in one of them, so f sub n is bigger than alpha strictly, but f sub n is less than or equal to the soup, so there you go. All right, and ta-da, the star of the show. A pointwise limit of measurable functions remains measurable. All right, okay, we're getting there. Okay, and note this one is for free, because if you converge, you're equal to your limit pointwise, but we know limits are equal to your lim sup. There you go, we're done. Look at that. Pretty cool, right? Okay. Okay, with that, that's it for measurable functions and sets. So next time we'll talk the Borel measurable ones, so we'll actually construct a specific sigma algebra to investigate, and that'll set the stage for getting integration going. So, cool stuff.